So here we're going to talk about hybridization of atomic orbitals. So the hybridization of s and p orbitals, and then also the hybridization of sp and d orbitals. So this is bridging off of valence bond theory and how valence bond theory, like I had alluded to, didn't do a great job in terms of justifying molecular geometry, not like Vesper could. So hybridization of atomic orbitals is the way in which we can bridge that gap. So this is what we mean by hybridization of s and p orbitals. So here is beryllium, and actually we say beryllium with a little asterisk next to it. That means it's in its excited state. So we've put one of those 2 electrons into the 2p orbital. So here is the normal electronic configuration that we're familiar with, right? Where we have a 2s orbital and then 3 2p orbitals. Hybridization is the process in which we essentially are combining those 2 orbitals together into an sp orbital. So we call that an sp hybridization or sp hybridized orbital. If you have 2 atomic orbitals that you are combining together, which we're doing here, a 2s and a 2p orbital, those are 2 orbitals. So we should create 2 hybridized orbitals. So the number of orbitals will never change in doing this hybridization process. And likewise, you can leave some of these orbitals outside of the hybridization process. So you can see those 2p orbitals on the right-hand side, those were left unchanged. So those were not a part of the hybridization process, so they remain unchanged. And this will become important later. So these 2p orbitals and these 2p orbitals are separate. Again, likewise, we have 2 orbitals here that we're combining together for 2 orbitals here. This is what this actually looks like. Here is the 2s atomic orbital and a single 2p atomic orbital. We are mathematically combining these 2 atomic orbitals together, and this is actually what you get for that for these 2 sp orbitals. So here were 2 orbitals, here are again 2 orbitals. So here we have one of the sp orbitals that looks like this, and another sp orbital that looks like that. So that is an example of hybridization. What's interesting is this actually has a very similar geometry to the 2p orbital because the 2s orbital is spherical. So if you take a look at these 2 orbitals, this s and this 2p orbital, you combine those together to form the sp orbitals, and they actually look very, very similar to those original 2p orbitals. So they end up being 180 degrees from each other, which we'll find is a very important aspect, which is similar to the geometry of this singular p orbital, in this case the px orbital, right? Where the py and the pz are left unchanged. This is the py and the pz, for example. So if we look at a molecule that has this situation occurring, here we have beryllium with 2 chlorines, let's say, attached to it. So just like the valence bond theory before, we're going to have positive orbital overlap between a p orbital from, let's say, this chlorine. But now we're going to have positive orbital overlap with the sp orbital on the beryllium. So here's orbital overlap with one of the sp orbitals. So that's this, let's say, this sp orbital, okay? And the other one, let's say it's this sp orbital. Okay? So we're going to have positive orbital overlap like we did before to form these chemical bonds. Here are the chemical bonds that we're observing. Again, it's important that these were 180 degrees to each other. This is 2 electron domains. Beryllium has no lone pairs on them. We don't see any lone pairs. There's no paired electrons, singular paired electrons here, or sorry, singular lone pairs here. So this beryllium has no lone pairs, so this is linear, and that's what we observe. This is the Lewis dot structure, and that's the molecular geometry. Beryllium could have only 4 valence electrons. That was one of those exceptions to an octet rule. Okay, so an sp hybridization results in linear molecular geometries here. We can do this again. Now let's do this for boron. So we're adding just 1 extra electron to the mix. So here is boron in its ground state electronic configuration. Here's the orbital diagram. what we're doing is we're exciting that electron. That's why we're now B star, and just adding a little energy. So now these electrons look like this. And we're going to take those 3 orbitals now and combine them together, meaning hybridize them. So we're going to have one of these s orbitals and 2 of these separate p orbitals coming together. That's where we get sp2 from. Okay, so there's a singular s and then 2 p orbitals that are combined together to get our 3 sp2 orbitals. Okay, so we're mixing 1 s orbital and 2 p orbitals, therefore yielding 3 total sp2 orbitals. This 2p orbital is again left untouched, so we're just leaving it as such. This is what this looks like. So mathematically, we're adding together a 2s, a 2p, and another 2p to get sp2. And this is actually 3 different sp2s. This is one of them, this is the other one, this is the third one. Okay. So they look, again, kind of like a little bit of a dumbbell, except the dumbbell is... so it looks kind of like a p orbital, but the dumbbell is much larger on one side than it is the other. And as you can see here, they're 120 degrees from each other. So again, this is what this looks like. Instead of accounting for an atom that has an s orbital and these 2 separate p orbitals, let's say a px and a py, we can combine those 3 orbitals together, i.e. hybridize them to undergo hybridization to form these sp2 hybridized orbitals. And again, this is what these would look like. They would be in the p, they'd be along the xy plane, and they'd be 120 degrees from each other. Along the z plane, we still have a 2p orbital, the 2pz, that's floating along this z in the z direction. So this results in, you might have guessed already, we see 120 degrees and there's 3 things. That's trigonal planar. So we actually get a similar sort of setup that we've observed before. So let's see boron trifluoride. That has a molecular geometry of trigonal planar, and this undergoes an sp2 hybridization. So here we have boron, and we're getting this 120 degree geometry. So this is starting to justify the geometry. We couldn't have done that with this. These are 90 degrees to each other. So this would not have justified if we had talked about valence bond theory with this ground state electron configuration. That would not have given us the correct geometry. We know it's trigonal planar due to our VSEPR theory understanding. And now hybridization of atomic orbitals in conjunction with valence bond theory can start to justify the geometries that we're observing. So again, we're going to have this sp2 hybridized orbital, this sp2 hybridized orbital, and this sp2 hybridized orbital overlapping with the valence electrons from a fluorine's electron. So in this case, this could be a p orbital, for example, right? So here we get the bond, valence bond overlap, these atomic orbital overlap with an atomic orbital here and a hybridized atomic orbital on the boron, these sp2 hybridized orbitals, to have positive orbital overlap in these 3 locations, which are the 3 single bonds that we're observing in the Lewis dot structure. Again, this is trigonal planar, so sp2 hybridization leads to a trigonal planar electronic geometry. And in this case, it's also the molecular geometry. All right, now you might have predicted we can go one step further. So here's carbon. This is the ground state of carbon. This looks like carbon will only bond twice if we had valence bond theory. So what we have to do is we promote these electrons just a little bit to get them ready for bonding. So they're all unpaired electrons. So we have a 2s orbital and then 2p3, so all 3 all 3 unpaired electrons. So now we have 4 bonding locations that can occur. But again, these are all 90 degrees to each other. We don't observe carbon having 3 90-degree bonds and then 1 unknown bond angle, for example. So we can do the same sort of method here, hybridization. Since we're using 3 p orbitals total and 1 s orbital, we get 4 orbitals total that we're producing, sp3 orbitals, and there are 4 of them, and this is what that hybridization would look like. Again, mathematically, we're jamming together a 2s, a 2p, a 2p, and another 2p. So this is the px, the py, and the pz, and we get sp3 orbitals. And there's 4 of them, Each of them, again, look very similar to the sp2 orbitals and even the sp orbitals, where they're the kind of lopsided dumbbell. It's probably harder to see here, but these are all mutually 109.5. So I think you know where this is going. This is the tetrahedral geometry. So again, this looks like the three p orbitals that are together, and then the s orbital. That doesn't really justify the bonding situation for something like carbon, but if you hybridize them, you now get this mutual 109.5 degree bond angles, which is what we're familiar with. So this is what this looks like for something like methane. Again, we see that 109.5 degree bond angle. It's tetrahedral. Here you have carbon, and I have the sp3 hybridized orbitals that are all 109.5. That can very nicely overlap with the 1s1 orbital of hydrogen. So now this positive orbital overlap is creating our sigma bond, our single bonding situations between these carbons and hydrogens, all 109.5. So now we're getting a good justification, a good combination, I would say, between the molecular geometries that we already know to be the case from VSEPR theory and some understanding of the actual what's actually occurring with these atomic orbitals, where just valence bond theory didn't really take us all the way to getting to geometry. But if you have valence bond theory in conjunction with this hybridization of atomic orbitals, we can now get at the geometry once again. So this also is giving us the correct geometry. It gets more complicated, kind of unfortunately. We've gone up to 8 electrons already, so but we know that we can go beyond that, right? We have trigonal bipyramidal, and we have octahedral. That actually is going to start using d electrons. So here's phosphorus in its ground state. It has 5 valence electrons. We can put them into slightly higher energy levels, so they're all unpaired. We're going to hybridize all of these together, and as you guessed it, this is sp3d. Since we're incorporating one of these d orbitals, we hybridize 5 orbitals together. So here we get 5 hybridized orbitals. These are the 5 bonding locations that can occur. So this is PCl5. Here's phosphorus. It has 5 bonding locations from these 5 hybridized orbitals. They will get the exact same geometry that you would expect for trigonal bipyramidal. These will be 180 degrees from each other. These 3 equatorial chlorines will be 120 degrees from each other. Okay, so we do end up getting that if we were to jam these together. I won't show what that looks like, but you get the idea there. So this is 10 total electrons around the phosphorus. So again, it has to be the case where it can break the octet rule. And you can see kind of the methodology in which it is able to break that octet rule. Before, you only could have 8 maximum electrons in the s and the p orbitals. But we can get up to 10 or 12 pretty easily by getting into the d orbitals if the central atom is close enough in energy. And you can see this 3d is just the next energy level up. So it's actually not too challenging to get an electron into that location. Again, it is not its ground state, so it may require just a little bit of energy to do that, but it is certainly achievable. Okay, so this is called an sp3d hybridization, and it leads to trigonal bipyramidal geometries. Lastly, again, I'm sure you saw it coming, sp3d2. So adding just one more electron and one more orbital. I see there's an error here. These 2 electrons, there should be a up electron here and an up electron here, right? So we have 6 valence electrons total for sulfur. All of those can be ready for chemical bonding here. If we were to combine all of those together, we would get 6 sp3d2 orbitals. All 6 of them are mutually going to be 90 degrees from each other. So here is what is occurring. So we can describe this bond between sulfur and fluorine, for example, as the sp3d2 hybridized atomic orbital of sulfur is overlapping with a p orbital from the fluorine. Okay, so that orbital overlap is how we can describe one of these chemical bonds. And again, this was called molecular geometry octahedral. This was a little confusing. Octa, we know means 8, but this only has 6. An octahedron has 8 faces to it, but only 6 vertices. And that's what these are. These are the 6 vertices. So that's where octahedral comes from once again. Okay, so this is what this looks like. This is the summation of everything we talked about here. So number of electron domains of the central atom, whether it's 2, 3, 4, 5, or 6. This was linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. The hybridized orbitals that are needed in order to do these geometries are shown here. SP, so there's 2 domains, so SP, that adds up to 2 total domains. 3 is SP2, a single S and 2 Ps. If there's 4 electron domains, that will be an SP3 hybridized orbital needed. 5 SP3D, 6 SP3D2. So simply the number of orbitals that you are combining together will equal the number of electron domains on the central atom. So that seems fairly straightforward, but we really do need to know something about where these come from. It is a little funky that this is occurring, but it's taken us a little bit of a step beyond understanding atomic orbitals as simply s orbitals, p orbitals, or d orbitals. This idea that there is some sort of mixing that it can occur to form these different geometries is also a needed understanding here. So let's try one of these sample problems. So ammonia we know is trigonal pyramidal with an HNH bond of about 107 degrees, right? It's a little bit less than 109.5 because there is a lone pair on that central nitrogen. So let's describe the formation of 3 equivalent NH bonds and explain the angles between them. Give the electron domain geometry, molecular geometry, and hybridization of the bond angles. Okay. All right. So NH3 is something that we've dealt with enough times, but here we have NH3. I can draw the Lewis dot structure, which again is a decent spot to start anyway. Okay. And we know that this lone pair takes up quite a bit more space, and that's why we're getting this 107, this to be 107 degrees instead of 109.5. Okay. All right. So in its ground state, well, we can just deal with these. We're trying to look at these chemical bonds between the nitrogen and hydrogen. The hydrogen has a 1s1 electron that it is contributing to this chemical bond. The nitrogen is also going to have some sort of orbital, some sort of atomic orbital or hybridized atomic orbital that will be contributing an electron for this shared electron system, this covalent bond that's being formed between the nitrogen and hydrogen. Nitrogen in its ground state has 5 valence electrons, and that would normally be the 2s2 and 2p3, right? We know it has a helium center here. Okay, so this is the 5 valence electrons, but this is going to form a certain geometry. We have an electron domain geometry of 4, which is tetrahedral. So this has a tetrahedral electronic domain geometry or electronic geometry, but it's a trigonal pyramidal in terms of its molecular geometry. So tetrahedral means that it has 4 electron domains, which ends up meaning that it should have an sp3 hybridized orbital. Okay, remember there's sp3. And sp3, if you recall, that was the 109.5 idealized bond angle anyway, right? And that's what we know is associated with tetrahedral, which is what we have here. So this, when we're describing the bond between the nitrogen and hydrogen, this nitrogen has this sp3 orbital, and it's from the 2 total, but so 2 sp3 orbital. 2 is just the energy level here, the principal quantum number from it. We could probably exclude this 2. You could probably exclude this 1, right? But this is there's an s orbital from the hydrogen and an sp3 orbital from the nitrogen that is forming these bonds. And you can use Vesper theory to talk about why this is 107, right? We're just saying that this lone pair is taking up a little bit more space, and that's why we're observing less than 109.5. But the 109.5 does come from this sp3 geometry. Okay, so electronic domain geometry, again, was tetrahedral. Molecular geometry is trigonal pyramidal, The hybridization of that central nitrogen is sp3, and that's why we're observing bond angles similar to 109.5. So this is how we would go about doing a problem like this, and how we can start talking more specifically about that chemical bonding interaction. Instead of just describing a chemical bond as ionic or covalent, we took it a step further and said, okay, there's covalent and polar covalent. Now it's a lot more detailed in terms of actually talking about what atomic orbitals or hybridized atomic orbitals are interacting to form that chemical bond.